The James Webb Space Telescope was supposed to help us see the early universe more clearly. Instead, it may be showing us that we understood far less than we thought. That is the uncomfortable tension at the heart of modern cosmology. Webb was not built to destroy our models. It was built to refine them, to look deeper, farther, and earlier than any telescope before it. To show us the first galaxies, the earliest light, and the young universe as it was beginning to take shape. That is exactly what Webb is doing. And the deeper it looks, the stranger the story becomes. Because some of the objects Webb is finding in the early universe do not look young enough. They look too bright, too structured, too mature, too massive for how little time should have existed. Webb has pushed the observable record closer to the Big Bang and confirmed extremely distant galaxies, including galaxies seen only a few 100 million years after the beginning. NASA also notes that Webb has continued finding surprisingly bright galaxies at these early times. That does not automatically mean the standard model of cosmology is wrong. But it does mean something is under pressure. And when reality begins to press against a successful theory, science enters its most interesting phase. So tonight, let us look carefully at why the James Webb Telescope is unsettling our picture of the universe, what it is actually finding, and why some astronomers are starting to ask whether our cosmic timeline is too simple. First, Webb is seeing galaxies earlier than many people expected. This part is easy to misunderstand, so let us be precise. The universe is about 13.8 billion years old. For a long time, astronomers expected that the earliest galaxies would begin small, irregular, dim, and chemically primitive. That is broadly still true in many cases. That alone is extraordinary, but early does not automatically mean problematic. The real pressure comes from what some of these galaxies seem to be like. Second, some early galaxies appear surprisingly bright and surprisingly evolved. Brightness matters because it can imply large numbers of stars, intense star formation, or structures that formed faster than expected. NASA says Webb has been finding surprisingly bright galaxies in the young universe, extending the pattern that earlier hints had already suggested. And when galaxies look brighter and more built up than expected at such early times, the question is no longer just how far back can we see? The question becomes, how did these things grow so fast? Did stars form earlier than our models assumed? Did matter collapse into galaxies more efficiently than expected? Were the first generations of stars unusually massive? Or are we misunderstanding what we are seeing? This is where Webb becomes dangerous to comfortable storytelling. Because the old picture of the early universe, as a simple, slow, gradual buildup, begins to feel less secure. Third, Webb is forcing astronomers to rethink reionization. After the Big Bang, the universe eventually cooled enough for neutral hydrogen to fill space. For a long period, that hydrogen acted like a fog, making the universe difficult for certain light to cross. Later, the first luminous sources began to reionize that fog. This period is called the era of reionization. Webb has identified many small galaxies as likely important drivers of that transformation, which is a major success. But it has also found at least one extremely early galaxy, whose bright hydrogen signal seems difficult to explain at such an early stage of that foggy universe. That is unsettling, because it suggests the early universe may not have changed over in the neat, uniform way we once imagined. Instead, reionization may have been patchy, messy, uneven, and locally intense. The universe may have been turning on in pieces. Fourth, Webb is making the first galaxies feel less primitive. Astronomers expected the earliest galaxies to be chemically simple and structurally immature. Yet Webb is finding evidence that even in relatively primitive environments, stars and interstellar material could produce dust earlier and more effectively than many people assumed. NASA reported Webb observations showing unexpected kinds of dust, even in a chemically primitive dwarf galaxy, strengthening the broader idea that cosmic enrichment may have started efficiently under harsher early conditions than expected. Dust may sound minor. It is not. Dust is part of the ecosystem of galaxies. It affects cooling, star formation, radiation, chemistry, and the visible appearance of whole systems. If the young universe was able to make dust, structure, and luminous galaxies faster than expected, then the first chapter of cosmic history may have been more productive than our simplest models allowed. Fifth, Webb is helping expose the difference between "we found something surprising" and "our theory is broken." This distinction matters a lot, because there is a temptation online to treat every Webb headline as proof that the Big Bang is dead or modern cosmology has collapsed. That is not what the official science says. Webb is not abolishing cosmology. It is refining it under stress. The standard model still explains a vast amount. The cosmic microwave background, large-scale structure, primordial abundances, and the broad expansion history of the universe. But within that success, there are tensions. And a tension is often how science announces the next layer of truth. Webb is not screaming that everything is wrong. It is quietly showing us that some pieces may be incomplete. Sixth, the Hubble tension has not gone away. This is one of the biggest reasons the conversation feels so serious. The Hubble tension is the mismatch between one expansion rate inferred from the early universe and another measured more directly in the later universe. In 2024, NASA reported that Webb and Hubble together affirmed that this puzzle persists. In 2026, NASA again described the disagreement as an ongoing major conundrum in cosmology. That does not mean Webb created the problem. But it does mean Webb did not rescue us from it. And when your most powerful telescope fails to smooth out a major cosmological tension, the message is unsettling. Maybe the data are trying to tell us something deeper about expansion, dark energy, distance measurements, or physics we have not yet understood. Seventh, Webb is changing the emotional meaning of the early universe. Before Webb, the first few 100 million years after the Big Bang were partly conceptual. We had models, indirect constraints, and a handful of fragile glimpses. Now that era is filling with actual objects, actual galaxies, actual structures, actual surprises. And that changes the feeling of cosmology. The early universe is no longer just the clean opening chapter of a theory. It is becoming a crowded crime scene. We are finding too many clues too early. And some of them do not agree neatly with the script we thought nature had written. Eighth, Webb is pressuring galaxy formation models from multiple directions at once. It is not just one weird galaxy. It is the accumulation of difficult cases, unexpected brightness, rapid star formation, unexpectedly early ionizing light, mature-looking structures, earlier assembly of very large systems. In early 2026, NASA highlighted a surprisingly mature galaxy cluster, assembling only about 1 billion years after the Big Bang, earlier than expected. That kind of result does not automatically destroy current theory, but it increases the sense that large-scale structure may have emerged faster in some regions than we anticipated. When several kinds of too early signals start appearing across different observations, theorists do not panic. But they do start rewriting assumptions. Ninth, Webb is showing that better observation does not always simplify reality. We like to imagine that a more powerful telescope gives cleaner answers. Sometimes it does. But sometimes a sharper instrument does something more disruptive. It removes our excuses. Before Webb, we could blame distance, faintness, and uncertainty. Now Webb is turning hidden epochs into observed terrain. And some of that terrain is not behaving. That is why this telescope feels so important. Not because it is merely powerful, but because it is powerful enough to embarrass easy explanations. 10th, Webb may be pointing us toward a more complicated universe than the one we taught ourselves to expect. Maybe the first stars formed earlier. Maybe feedback worked differently. Maybe small galaxies were more efficient at reshaping the young cosmos. Maybe massive black holes began growing sooner. Maybe some assumptions about early structure formation need to be loosened. Or maybe the standard model survives, but only after being made less elegant. That possibility matters too. Because science does not always move by replacing a theory completely. Sometimes it moves by making the theory more complicated, less comfortable, and more true. And that may be exactly where Webb is taking us now. If you are still here, subscribe. Because this channel is about the moments when science stops feeling tidy, when the universe becomes harder to summarize, and when new observations force old ideas into deeper questions. The James Webb Telescope is not breaking our understanding of the universe in the simple clickbait sense. It is doing something more interesting. It is revealing where our understanding becomes fragile. It is showing us galaxies where we expected shadows, structure where we expected simplicity, light where we expected fog, and unresolved tension where we hoped for closure. That is how real scientific revolutions often begin. Not with one dramatic announcement, but with a pattern, a cluster of stubborn observations, a growing feeling that the universe is not violating the rules, only exposing how incomplete our rulebook may be. So why is the James Webb Telescope breaking our understanding of the universe? Maybe because the universe was never required to become simpler, just because we finally learned how to look deeper. Maybe the deeper truth is the opposite. The better we see, the stranger reality becomes. And Webb is teaching us that the first light of the cosmos may not be the beginning of clarity. It may be the beginning of a much larger confusion. Somewhere in space, about 650 light years from Earth, there is a ticking clock, a cosmic one. When it reaches zero, it will unleash a wave of burning radiation and incandescent matter, racing through the Milky Way and tearing apart everything in its immediate path. Planets too close will be shredded. Rock will melt into magma. Atmospheres will be stripped away. And this ticking time bomb is close enough that, if you look up at the night sky, you can see it with your naked eye. It is one of the brightest objects above us. This star is Betelgeuse, our nearest red supergiant. And one day, it will explode as a supernova. The question is not if, the question is when. Centuries from now? Decades? Years? Or sooner than we expect. And when it happens, what does it really mean for Earth? To answer these questions, scientists have spent decades watching this volatile giant as it sways on the edge of annihilation, searching for signals that might reveal when its internal countdown finally reaches zero. And the closer we look, the more surprising Betelgeuse becomes. The basics, what we see in the sky. Let's begin with what we think we know. Betelgeuse is the 10th brightest star in the night sky. You can easily spot it as the left shoulder of Orion. Unlike the stars around it, Betelgeuse appears distinctly red, and it flickers noticeably. That color tells us something important. Betelgeuse is a red supergiant. These stars are vastly larger than our Sun, and Betelgeuse is no exception. Its radius extends beyond the orbit of Mars. If it replaced the Sun, it would swallow the inner solar system. It has nearly 900 times the radius of the Sun, yet only about 10 times the mass. That means its density is astonishingly low. Its material is spread so thin that gravity barely holds the star together. That's why enormous convection cells bubble across its surface. Vast regions of rising and falling plasma, each one larger than the orbit of Earth. Imagine standing on a planet orbiting a star like this, watching a sunset that stretches across a surface larger than the entire inner solar system. But of course, Betelgeuse isn't famous for its size alone. It's famous because it is dying. How dangerous is a nearby supernova? Supernovae are not rare in the universe. Astronomers observe hundreds every year in distant galaxies. But inside our own Milky Way, they are much less common. On average, we expect only 2 or 3 per century. That makes the odds of one exploding tomorrow fairly low, but not zero. So what would happen if one did? The answer depends on distance. Archaeological and geological evidence suggests Earth may have already experienced the effects of nearby supernova in the past. We currently reside inside a region of space known as the local bubble, a relatively empty cavity about 1,000 light-years wide. Many scientists believe this bubble was carved out by a supernova explosion between 10 and 20 million years ago, an event Earth may have witnessed. Other evidence points to another explosion around 2.5 million years ago, detected through unusual concentrations of radioactive isotopes embedded in Earth's geological record. These explosions were distant enough to spare us serious harm. But not all consequences may have been so gentle. Some researchers have even suggested that debris from a distant supernova could have contributed to the extinction of woolly mammoths around 13,000 years ago, though this remains debated. Still, one fact is undeniable. Life on Earth has survived multiple nearby supernova events, which raises an uncomfortable question. If supernovae are so destructive, why are we still here? Distance is everything. Supernovae are devastating, but only up close. Think of it this way. A nuclear explosion thousands of kilometers away is a spectacle. One on your nightstand is fatal. Fortunately, the universe has very large nightstands. To understand why, we need to understand how supernovae actually happen. Two ways a star dies. There are two primary paths to a supernova. Type Ia supernova. In one scenario, a dense stellar remnant called a white dwarf slowly steals matter from a nearby companion star. As it gains mass, gravity eventually overwhelms the internal pressure holding it together. Carbon fusion ignites. The star detonates. In seconds, it releases more energy than our sun will emit in its entire lifetime. Matter is hurled outward at 6% the speed of light, bathing the galaxy in intense radiation. Type II supernova, Betelgeuse's fate. Betelgeuse follows the second path. Massive stars burn through their fuel in stages. Hydrogen becomes helium. Helium becomes carbon. Carbon becomes heavier elements. Each cycle creates outward pressure that resists gravity. But there is a limit. Once iron forms in the core, fusion stops producing energy. Gravity wins. The core collapses. The outer layers rebound violently, and the star tears itself apart. This is the fate awaiting Betelgeuse. Would Betelgeuse harm Earth? Thankfully, no. At 650 light-years away, Betelgeuse is far outside the lethal radius. Studies suggest the death zone for atmospheric destruction lies within about 25 light-years. Even planets orbiting a star at distances 100 times farther than Earth orbits, the Sun could remain physically intact, though life would face severe challenges. Earth is protected not just by distance, but by the Sun's heliosphere, which acts as a massive magnetic shield. When Betelgeuse explodes, we will be safe. But we will see it. Possibly as bright as a full moon, visible even in daylight. A supernova blazing in our sky. When will it happen? Here is where certainty collapses. Astronomically speaking, Betelgeuse will explode soon. That could mean 100,000 years. Or it could mean within a few decades. Some studies suggest Betelgeuse may be larger than previously thought, which could place it closer to detonation than expected. But Betelgeuse refuses to give us a clear answer. The star that behaves strangely. Over the past century, Betelgeuse has displayed strange cycles of brightening and dimming. Some last hundreds of days. Others stretch over thousands. In 2019, the star suddenly dimmed dramatically, an event now known as the Great Dimming. At first, speculation exploded. Was this the prelude to a supernova? Later observations suggested the dimming was caused by a massive cloud of dust expelled by the star, temporarily blocking its light. But the event reignited interest and revealed something unexpected. Does Betelgeuse have a companion? For over a century, scientists wondered whether Betelgeuse might have a small companion star. Detecting it was incredibly difficult. The surface of Betelgeuse is chaotic, turbulent, and constantly shifting. But recent analyses of long-term data revealed subtle, repeating motions, as if Betelgeuse were being gently pulled back and forth. This suggests the presence of a smaller stellar companion, orbiting closer than Saturn orbits the Sun. If confirmed, this companion could explain some of Betelgeuse's strange cycles. But confirmation will take time. Astronomy rewards patience. The rotation mystery. Another puzzle lies in Betelgeuse's rotation. Measurements suggest the star may rotate once every 20 years. That might sound slow, but for a star this large, it is astonishingly fast. Too fast. According to known physics, a supergiant of this size should rotate far more slowly. So what's happening? One possibility is stellar cannibalism. Betelgeuse may have consumed a companion star long ago, stealing its angular momentum. Another possibility is more unsettling. The rotation may be an illusion. Betelgeuse's surface is dominated by enormous, turbulent plasma bubbles, some spanning 100 million kilometers. Their motion alone could create Doppler shifts that mimic rotation. When resolution is limited, chaos can masquerade as order. And Betelgeuse may be fooling us. Waiting for answers. Higher resolution observations are already underway. But analysis takes time, years, not months. Until then, we are left with questions. Is Betelgeuse spinning at impossible speeds? Or is its surface turbulence deceiving us? Is it closer to explosion than we think? Or safely ticking away for millennia? Betelgeuse is a star on the brink of catastrophe, yet it poses no threat to Earth. Instead, it offers something else. A reminder that the universe is violent, beautiful, unpredictable, and far less obligated to make sense than we would like. When Betelgeuse finally explodes, it will be a spectacle beyond imagination. And when it does, we will be watching. A dangerous idea. What if the universe is not a machine, but a living being? What if everything we call matter, stars, galaxies, even us, are just cells in something far greater? It sounds like philosophy, but the James Webb Space Telescope might have just given us a reason to take that idea seriously. For decades, cosmologists believed the early universe was silent, a cold stage where stars flickered mechanically into existence. But Webb is showing us something else entirely. It's messy, it's turbulent, and it's moving with a rhythm that feels alive. Everywhere Webb looks, galaxies twist like nerves, gas pulses like breath, and light itself behaves like a heartbeat. So the question is no longer just, how did the universe begin? Maybe it's, what if the universe never stopped beginning? The universe that breathes. Webb's infrared eyes peer into time, billions of years back, and what it sees doesn't look peaceful at all. Instead of static galaxies calmly rotating, it sees explosions, collapses, violent bursts of energy, and through that chaos, a strange pattern. Every few million years, waves of light surge outward, then fade, nebulae expand, then contract. It's as if the universe is inhaling and exhaling. Scientists call it cyclic energy release, but to some, it looks eerily like respiration. The cosmos breathing through radiation, its light flickering in the dark. When you watch the time-lapse reconstructions from Webb data, it feels like watching a living organism under a microscope. Every star a neuron, every filament a blood vessel, every pulse a heartbeat. And maybe that's not just poetic metaphor. After all, if galaxies follow self-organizing patterns, if energy moves in rhythmic waves, and if the universe constantly renews itself, how different is that from life itself? So, are we inside a living being? Or is life just the universe learning how to look back at itself? The hidden energy fields. James Webb's instruments can't see dark energy or dark matter directly, but they can feel their fingerprints. Between galaxies, where we thought there was nothing, Webb detects faint gravitational ripples, invisible currents shaping everything. What holds the cosmos together? Something unseen, something everywhere. Call it dark energy, call it the cosmic nervous system. Either way, 95% of the universe is invisible, and yet it's what makes the visible possible. The galaxies don't float randomly. They're connected, bound by an invisible network that looks shockingly like the neural web inside a human brain. Coincidence? Or symmetry on a cosmic scale? One recent simulation compared the density of galaxies in the universe with the density of neurons in the brain. They found both systems, brain and cosmos, store information the same way. So if the human brain can think, what does the universe do? Galaxies in motion. The most shocking thing Webb revealed isn't how galaxies look, it's how they move. Everywhere motion. Spirals, collisions, mergers, streams of plasma, a cosmic dance of destruction and creation. But there's something deeper. It's not random. When galaxies collide, they form new order. When stars explode, they create new elements. Every act of chaos feeds the next generation of structure. That sounds a lot like evolution. We thought evolution was only for biology, but maybe the entire universe evolves. Maybe galaxies compete, grow, adapt, not to survive, but to express energy more efficiently. And if that's true, then the universe isn't a dead mechanism of matter and laws. It's a self-learning, self-correcting system, a living cosmos, aware through the movement of its own light. The cosmic mind. There's a saying among physicists, the universe is under no obligation to make sense to you. But what if it does? What if the patterns we see, spirals, fractals, symmetry, are not coincidence, but cognition? Webb's deep field images show galaxies arranged in filaments and nodes like synapses. They transmit light, energy, and information, just as neurons transmit impulses. Each pulse of light carries not just energy, but data. In a sense, light is the language of the universe. And we, human beings, are simply one of the ways it has learned to speak. When we build telescopes like Webb, we're not observing the universe from the outside. We're the universe, studying its own reflection. The living light. Everything alive glows. Stars, cells, even the human brain emit faint light when they process energy. And when Webb observes the universe, it finds light behaving in ways that mimic metabolism, constantly absorbed, transformed, released. Light is not just illumination, it's creation. Every photon Webb records has a history, born in the heart of a star, scattered across time, and finally captured by a golden mirror floating in darkness. So when Webb sends us those glowing red and purple images, we're not just seeing light, we're seeing memory, the afterimage of creation itself. And that means, in some strange way, the universe remembers. The universe becoming aware. Here's the most unsettling thought of all. If the universe evolves, breathes, and learns, then consciousness might not be a human trait. It might be a universal process. Maybe stars don't think the way we do, but maybe they feel through gravity, through light, through connection. Every atom in your body was forged inside a star. Every spark of your thought is powered by cosmic energy. So when you look up and wonder who's out there, maybe the universe is wondering the same thing about you. It's alive. So is the universe alive? Science will say, not yet. But James Webb's discoveries whisper a different answer. Because everywhere Webb looks, in every glowing nebula, every filament, every pulse of light, the universe looks back. And maybe, just maybe, it's finally starting to recognize itself. What if the universe is not strong, but fragile? What if, hidden in its vast beauty, are cracks that could destroy everything? When we look into the silent night sky, humanity is confronted with the greatest mystery of all. Why are we here? And why does the universe exist the way it does? For centuries, astronomers and philosophers have tried to peel back the cosmic veil. Each answer, however, revealed not closure, but deeper riddles. Today, with telescopes capable of gazing billions of years into the past, we can see light that began its journey before Earth had even formed. And yet, the more we see, the more fragile the universe appears. Hidden in its vastness are points of weakness, phenomena so strange, so uncompromising, that they could unravel reality itself. Could the universe itself one day collapse, not because of outside forces, but because of its own weaknesses? Physicists give them different names: black holes, dark matter, unstable particles. But the meaning is the same. The universe is not a fortress. It is a puzzle built on delicate balances, and the smallest disruption might shatter it. Black holes, the universe's hidden wounds. A monster so powerful that even light cannot escape. Black holes are not just cosmic objects. They are wounds in reality itself. Imagine an object so heavy that not even light can escape. A place where time slows to a crawl, and the laws of physics collapse into silence. This is the black hole, once a wild idea of theory, now a photographed reality. The Event Horizon Telescope gave us the first shadow of one, but a picture of darkness only deepens the mystery. What lies beyond that edge? From the outside, a black hole appears as a hungry void wrapped in a swirling ring of fire, an accretion disk of matter falling into oblivion. Gas and stars are torn apart, heated to unimaginable temperatures before vanishing forever. But here is the enigma. Inside the event horizon, the rules of our universe break down. What really happens beyond the event horizon, another universe, or the end of everything we know? If black holes are the weak seams of the universe, then reality itself is stitched together by fragile threads. And somewhere, perhaps, those threads may begin to tear. Cosmic wanderers, comets and asteroids, Small, silent, unstoppable. Cosmic wanderers have rewritten Earth's story before, and they could do it again. If black holes are the monsters of the universe, then comets and asteroids are its restless wanderers. Small, silent, but carrying the power to change everything. How many times has Earth's story been rewritten by a rock from space? The most famous event was the asteroid that ended the age of dinosaurs, but it was not the only one. Countless impacts shaped continents, oceans, even the evolution of life. What if another asteroid is already on its way, and we simply haven't seen it yet? And today, we know this danger is not behind us. Every year, thousands of objects sweep past Earth, some harmless, others terrifyingly close. One miscalculation, one unlucky trajectory, and our world could change in an instant. But comets and asteroids are more than threats. They are messengers. Made of ancient ice and stone, they carry the memory of the early solar system. Some scientists even believe that the water in our oceans, and perhaps the first building blocks of life, were delivered by these cosmic travelers. Still, not all wanderers are familiar. Strange elongated objects like Oumuamua pass through, leaving astronomers stunned. Others glow with mysterious auras, like Atlas, a comet some once called alive. Each of them whispers a story about a universe that is not stable, but dynamic, unpredictable, fragile. The invisible threads, particles, and fundamental forces. At the smallest scale of existence lies the greatest danger. A single unstable particle could erase the universe. We are used to thinking of the universe as galaxies, stars, and planets. But at its foundation, everything reduces to the tiniest building blocks, particles. Invisible, yet powerful enough to shape the cosmos. For decades, physicists chased one of the most elusive of them all, the Higgs boson, sometimes called the God particle. Its discovery in 2012 confirmed that particles gain mass through an invisible field that permeates the universe. Without it, there would be no atoms, no stars, no life. But here lies the danger. The Higgs field may not be stable. Some theories suggest that the universe exists in a false vacuum, like a bubble waiting to burst. One day, a quantum fluctuation could trigger its collapse, rewriting the laws of physics in a catastrophic instant. What if the Higgs field collapses tomorrow? Would the universe vanish in an instant without warning? Other mysteries lurk at the quantum scale. Particles appear and vanish in empty space, creating a restless quantum foam. Forces that should explain everything instead raise more questions. Why is gravity so weak compared to other forces? Why does dark matter outweigh normal matter, yet remain invisible? Could unseen particles be tunneling between dimensions? These questions are not academic. If the balance of these forces shifts, even slightly, the stars would not burn, galaxies would not form, and life would never exist. The smallest particles may carry the greatest weaknesses of the universe. final balance, collapse or harmony. The universe is not eternal. It is balanced on a knife's edge between survival and destruction. When we weave together all these threads, black holes, cosmic wanderers, unstable particles, a haunting picture emerges. The universe is not eternal. It is not unbreakable. It is fragile. Black holes threaten to consume everything near them. Asteroids remind us that survival is never guaranteed. Quantum fields whisper that reality itself may be temporary, balanced on a razor's edge. And yet, here we are. Somehow, against impossible odds, life exists. Our planet orbits in a safe zone. Catastrophes have shaped, but not ended, our history. Even the weaknesses of the universe seem to conspire toward creating the possibility of consciousness, the ability to ask these very questions. Are we living in a universe that is destined to fall apart, or one designed to create life through its very weaknesses? Perhaps that is the true revelation. The universe's fragility is not its flaw, but its design. Its weaknesses are the openings through which life, thought, and meaning enter the cosmos. Still, the story is unfinished. At any moment, the balance could break. Another comet may strike. A black hole may wander closer, or the Higgs field may tremble. But until then, the fragile universe endures, vast, mysterious, beautiful. And within its weaknesses, we find our greatest strength, the drive to understand it. The universe may be fragile, but as long as it endures, so does our search for meaning among the stars. Imagine just for a moment that everything you know, the street you walk on, the tallest mountain you have ever seen, the entire world that feels solid beneath your feet, is nothing more than a speck of dust suspended in an endless void. We live our lives anchored to the ground, worry about traffic, deadlines, or tomorrow's weather, rarely stopping to realize that we are standing on a small blue marble racing through space at unimaginable speed, drifting inside a vast, silent ocean of darkness. The scale of the universe is not just large, it is unsettling. If you tried to measure the cosmos using the rules of everyday life, your intuition would collapse. Distances lose meaning. Time stretches, bends, and behaves in ways the human mind was never designed to grasp. So let's step outside our comfort zone. Let's leave behind the fragile protection of Earth's atmosphere and confront a difficult idea. We are a biological accident inside an immensity with no visible borders. And from the moment we lift off, reality begins to distort. What looks like a calm, star-filled sky is, in truth, a battlefield of immense forces. Exploding stars powerful enough to erase entire systems. Regions so empty that light takes eons to cross them. This is not science fiction. This is the raw structure of the universe we inhabit. And here comes the uncomfortable question. If this is reality, why does our everyday world feel so small, so stable, so safe? Perhaps because we were never meant to sense the true scale of existence. As we begin this journey, from the doorstep of our homes to the very edge of what can be observed, there is no turning back. Once you understand where we truly are, the world never feels quite the same again. Before we go any further, ask yourself, have you ever truly grasped how far, far really is? Leaving Earth's atmosphere, the first thing that becomes painfully clear is how fragile our bubble of life really is. If Earth were shrunk down to the size of a 1 centimeter marble, the Moon would orbit it at about 30 centimeters away, like a tiny pebble floating nearby. At human scale, this feels manageable. In reality, the Moon sits nearly 384,000 kilometers away. It took Apollo astronauts 3 full days of continuous travel to cross that distance, moving through a vacuum filled with radiation and magnetic forces that Earth's atmosphere normally shields us from. And this is only the first step. Beyond the Moon, distance stops behaving intuitively. Light, the fastest thing in the universe, takes just over a second to travel from Earth to the Moon. But reaching the Sun? 8 minutes and 20 seconds. Think about that. If the Sun were to disappear right now, we wouldn't know for more than 8 minutes. We live in the past, even on a cosmic scale this small. The Sun is not just a star. It contains more than 99% of all the matter in our solar system. A natural fusion reactor holding planets in an endless gravitational dance. And yet, even this giant is just another stop on a much longer road. Movies often show asteroid belts as dense minefields. Reality is far more disturbing. Space is so vast that if you stood on an asteroid in the belt, you might not see another one at all. They are separated by millions of kilometers. This raises an unsettling thought. Is the universe mostly stuff or mostly nothing? The answer is clear. We are tiny points of matter floating in an overwhelming sea of emptiness. Jupiter and Saturn follow. Gas giants so massive they could swallow Earth thousands of times over. Jupiter's Great Red Spot, a storm larger than our entire planet, has been raging for centuries. And yet, even these giants are merely rest stops. Beyond Uranus and Neptune, the Sun shrinks into a brilliant dot. Warmth disappears. Darkness begins to dominate. We enter the Kuiper Belt, a frozen graveyard of ancient debris, remnants from the birth of the solar system over 4.5 billion years ago. Human technology struggles here. The Voyager probes, launched in the 1970s, have traveled for decades at more than 60,000 kilometers per hour, and only now are they beginning to leave the Sun's influence. Let that sink in. Everything we call a long journey on Earth is barely a blink in cosmic terms. And astonishingly, we still haven't left home. Far beyond lies the theoretical Oort cloud, a vast spherical halo of icy bodies surrounding the solar system. Reaching its outer edge would take thousands of years with our current technology. Here, the idea of the solar system becomes something far larger than most people imagine. Distances are no longer measured in kilometers, but in astronomical units. The Oort cloud may extend up to 100,000 astronomical units from the Sun, so far that solar gravity barely holds it together. At this boundary, the Sun becomes just another star among hundreds of billions. Crossing into interstellar space forces a brutal realization. Everything humanity has ever done happened in a region so small. It vanishes from view at the edge of our own system. We are not central. We are not special. We are inhabitants of a quiet suburb orbiting an average star. And beyond that suburb lies a void the human brain was never designed to process. No up, no down, no directions. Just distance in every direction. Our galaxy, the Milky Way, stretches over 100,000 light years and contains hundreds of billions of stars, most of them with planets of their own. At its center lurks a supermassive black hole, Sagittarius Asterisk, with a mass of 4 million suns, anchoring the entire system in a slow gravitational dance. And yet, even this galaxy is just one among many. The Milky Way belongs to the local group. The local group belongs to a cluster. The cluster belongs to a supercluster. At the largest scales, galaxies form filaments in voids, a cosmic web so vast it resembles a neural network on unimaginable scales. This raises a profound question. Is the universe structured? Or is structure simply what gravity leaves behind? When we look far enough, we are not just looking across space, we are looking back in time. Light from distant galaxies began its journey before Earth even existed. The universe becomes a natural time machine. At the very edge of what we can observe, we encounter the oldest light of all, the cosmic microwave background, the afterglow of the Big Bang itself. This is the universe as it was only 380,000 years after its birth. No stars, no planets, no life, just the blueprint of everything to come, and beyond that, nothing we can see. Not because nothing exists, but because light has not had enough time to reach us. This is the observable universe, a boundary defined not by space, but by time. And here lies the final, unavoidable question. What exists beyond the horizon of observation? Science offers no answers based on belief, only models, mathematics, and limits. Perhaps the universe is infinite. Perhaps our universe is just one bubble among many. Perhaps reality is far stranger than we can currently imagine. What we do know is this: only about 5% of the universe is made of ordinary matter. The rest is dark matter and dark energy, invisible forces shaping everything we see. We are living inside a structure dominated by things we cannot directly observe. And yet, somehow, within this vast emptiness, consciousness emerged. The scale of the universe teaches a brutal lesson in humility. We are not the center, we are not the purpose, but we are the part of the universe that learned how to look back at itself. Every telescope we launch, every observation we make, pushes the curtain back just a little farther. And even if the universe remains mostly empty, mostly dark, and mostly indifferent, our desire to understand it may be the most extraordinary thing it has ever produced. The journey does not end here. It only gets bigger.